a small team of engineers in Huntsville, Alabama, fired a rocket engine for 300 seconds straight, 4,000 pounds of thrust, and when they shut it down and looked at the hardware, no damage. None. Here's the thing, that should not be possible. Rocket engines are violent machines. They burn at thousands of degrees, they shake themselves apart, and after every test fire, engineers spend weeks inspecting for cracks and erosion to identify microscopic damage or thermal stress. But this engine came out clean. And the reason it came out clean is the same reason it is fundamentally different from every engine that has ever flown. It doesn't burn fuel, it detonates it. And the physics of that one difference changes everything. I'm talking about rotating detonation engines, RDREs. And if the math holds and the test data so far says it does, this is the first genuine paradigm shift in chemical rocket propulsion since the Apollo program. Not 5% better, not 10% better, potentially 25% more efficient. And of course, there's a global race happening right now to build them. The US, China, Japan, India, everyone with a space program is chasing this. First, we need to talk about why conventional rocket engines have hit a wall, because to understand why the RDRE matters, you have to understand the problem it solves. Rocket engines today work the same fundamental way they did in the 1960s. You take fuel, you take an oxidizer, you spray them into a combustion chamber, you ignite them, the hot gases expand and rush out of the nozzle. And, of course, the rocket moves forward. It's called deflagration subsonic combustion. The flame front moves at meters per second. It's slow in combusting terms. It works. It got us to the moon, but it's inherently inefficient. And here's why that matters more than you might think. There's a thing called the rocket equation. To carry more payload, you need more fuel. More fuel means a heavier rocket. A heavier rocket needs more fuel to lift that fuel. So it's quite the cycle. This is why rockets are 90% fuel tanks by mass. The Falcon 9 at liftoff is basically a giant aluminum can full of kerosene and liquid oxygen, with a tiny payload on top. And we've spent decades and billions of dollars trying to squeeze more efficiency out of these engines. Chamber pressures have gone up, materials have gotten better. As an example, the Raptor 3 engine from SpaceX is an absolute masterpiece of incremental engineering. 280 tons of thrust, record chamber pressures, but the harsh truth is, the fundamental efficiency of a chemical rocket engine, measured as specific impulse, has barely moved in 60 years. You can tweak materials, you can push chamber pressures, you can optimize nozzle geometries, but you are still burning fuel subsonically. And the physics of subsonic combustion has a ceiling. You hit it, everyone hits it, because it is dictated by the speed of sound. Which raises a question. What if instead of burning the fuel, you could detonate it? That's not a rhetorical question. A detonation releases energy up to 25% more efficiently than a deflagration. The fuel releases more of its chemical energy. The exhaust velocity is higher, and the engine can be smaller, lighter, and produce the same thrust. The problem? Detonations are uncontrollable by nature. They're what happen when engines fail. A detonation in a conventional rocket engine is called a hard start, and it usually means your engine becomes a crater. So how do you contain a continuous supersonic detonation and turn it into thrust? That question has been sitting on propulsion engineers' desks since the 1950s, and it took until 2025 for someone to answer it convincingly. Okay, let's actually understand what's happening inside of one of these engines. This is where it gets genuinely elegant. In a conventional rocket engine, you have a cylindrical combustion chamber. Fuel and oxidizer spray in from the top. They burn steadily, hot gases flow out at the bottom through a nozzle, steady, continuous subsonic combustion. A rotating detonation engine looks different. The combustion chamber is not a cylinder, it's a ring, and an annular channel. Picture a donut, or better, a circular racetrack. Fuel and oxidizer are injected continuously around this ring, and then something wild happens. The one ignition event starts a detonation wave. That wave then chases itself around the ring. As it passes each section, it detonates the fuel waiting there. The explosion forces hot gas out the open end of the ring, producing thrust, and the energy from the detonation pushes the wave forward right as new fuel is being injected ahead of it. The wave sustains itself continuously, around and around. You are literally containing a continuous supersonic explosion and extracting useful work from it. And the detonation wave moves so fast, thousands of meters per second, that it completes multiple laps around the ring in the time it takes you to blink. Astrobotic's Chakram engine, the one that just broke the record, had 3 detonation waves chasing each other simultaneously around the ring. 3 combustion events per rotation. Higher frequency means smoother thrust. More power density, and that's the key phrase here, power density. Because a detonation releases more energy per unit of fuel, and because the combustion happens in this compact ring rather than a large cylindrical chamber, an RDRE produces more thrust per kilogram of engine mass than a conventional engine. Smaller engine, same thrust. That means a lighter rocket overall, which means less fuel needed when this breaks the vicious cycle of the rocket equation. There's another advantage that pairs naturally with this design. Most rocket engine nozzles, the bell-shaped part at the bottom, are optimized for one altitude. A sea level nozzle is inefficient in vacuum, and a vacuum nozzle is inefficient at sea level. It's why upper stages have those massive nozzle extensions that would tear apart at low altitude. An RDRE pairs beautifully with something called an aerospike nozzle. Instead of a bell nozzle, an aerospike is essentially an inverted cone or ramp. The exhaust flows around the outside of a central spike, and the ambient air pressure acts as the outer wall of the nozzle. At low altitude, the air pressure constrains the exhaust. At high altitude, the exhaust expands naturally. It's self-adapting, efficient everywhere. Now combine an RDRE with an aerospike and you get an engine that's fundamentally more efficient than anything flying today, at every altitude across the entire flight envelope. The theory is elegant, the potential is enormous, and people have known about this concept since the 1950s. So why did it take until 2025 for the team to fire one for 5 continuous minutes? The answer is material science, thermal management, and a bet that almost nobody was willing to take. Until now. So the company that just broke the world record for the longest RDRE burn is not SpaceX, it's not Blue Origin, it's not a defense contractor with a black budget and unlimited resources. It's Astrobotic, a company based in Pittsburgh, Pennsylvania. They're a lunar lander company. They built the Peregrine lander, and back in 2024, Peregrine launched on the first Vulcan Centaur rocket. It didn't make it to the moon, but that's a different story. The point is, Astrobotic knows propulsion. They need better engines for their next generation lunar missions. And they made a bet that a rotating detonation engine was the answer to the future. They partnered with NASA Marshall Space Flight Center in Huntsville, Alabama. NASA provided the test infrastructure. NASA has been quietly funding RDRE research for years. They knew the potential. They just needed the right partner who was willing to take the risk. And this is what the test campaign looked like. 2 Chakram engine prototypes, 8 successful hot fire tests, more than 470 seconds of total runtime, a 300-second continuous burn, which is believed to be the world record for the longest RDRE firing. Each engine produced more than 4,000 pounds of thrust, and this is the part what made engineers stop what they were doing. 0 discernible damage to the engine hardware. Let me emphasize why that last part is so significant. Previous RDRE tests worldwide typically ran for seconds, maybe tens of seconds, because the detonation environment is brutal. You're containing continuous supersonic explosions. The thermal loads are just extreme. The vibrational environment is unlike anything a conventional engine experiences. Components crack, materials fall, tests end. Astrobotic's engine ran for 5 minutes and came out completely clean. That means the material science cracked a problem that had killed everyone else's tests before them. They figured out how to manage the heat load, how to dampen the vibrations, and how to make the thing survivable. And the team that did this, not a massive operation, in their own words, quote unquote, a small team working across multiple offices on a very modest budget. One engineer from the program said, and this is a quote, "To achieve such a historic milestone on our first try, that was just incredible." First try. The test itself is worth understanding at a technical level. They tested at NASA Marshall because Marshall has the infrastructure for high-pressure propellant systems and the safety protocols for experimental engines. The Chakram engine used what's called a GOX methane propellant combination. Methane is the future of rocket propellant. SpaceX's Raptor engine use it, Blue Origin's BE-4 uses it, and Astrobotic has chosen to use it too. It burns cleaner than kerosene, which means less residue and better reusability. But Astrobotic isn't the only player in this game. While they were breaking records in Alabama, something else was happening on the other side of the world. And when you map out who's working on Detonation engines and why, it starts to look less like a research curiosity and more like an arms race. Let's start with Japan, because Japan was first, at least first to test an RDRE in space. In 2021, JAXA, the Japan Aerospace Exploration Agency, launched a rotating detonation engine on a sounding rocket, S-520-31. The RDRE was a small demonstrator, about 500 newtons of thrust. Tiny compared to Astrobotic's 4,000-pound engine, but it fired successfully in flight conditions. First detonation engine ever to operate in space. Japan's interest is clear. They're targeting RDREs for upper stage engines and deep space missions. A more efficient upper stage means more payload to the moon or to asteroids. And Japan, like many space agencies, is operating on a budget, so efficiency matters. Now, China. China is harder to track because they don't publish like Western agencies do. But open source intelligence and academic papers tell a consistent story. Multiple teams at Chinese universities and defense laboratories are working on detonation propulsion. The Chinese Journal of Aeronautics published a paper in 2023 titled Progress of Rotating Detonation Engine Research in China, and it described experimental RDREs operating on hydrogen, ethylene, and kerosene. The motive for China is twofold. One, responsive space launch, the ability to put satellites into orbit quickly. Two, and more likely the primary driver, hypersonic weapons. An RDRE-powered cruise missile at Mach 5 is a game changer for military technology. Compact engine, high thrust, wide throttle range. China's military programs and their space programs overlap heavily in propulsion. When they move fast, and they don't publish until years later. India is the dark horse in this race, and maybe the most interesting story. D-Propulse Aerospace, founded by Saurav Jha, who previously ran Delhi Defense Review, a defense analysis publication. He transitioned from analyzing India's aerospace gaps to building hardware to close them. The team includes Dr. V.K. Saraswat, a former chairman of India's Defense Research and Development Organization, Dr. V, a former DRDO scientist who worked on India's scramjet program, Professor S.R., a combustion expert from IIT Madras. In under a year, D-Propulse tested a rotating detonation engine producing around 5 kilonewtons of thrust. Paired with an aerospike nozzle, that is a remarkably fast turnaround from company founding to hot fire test. India sees RDREs as a way to skip decades of conventional engine development. The Kaveri engine, India's indigenous fighter jet engine, has been in development for decades and is still not operational. With an RDRE, you leapfrog. You don't spend 30 years catching up, you bet on the next generation and try to get there first. And the US? Beyond Astrobotic, it's an ecosystem approach. NASA in-house research, DARPA programs, Pratt & Whitney, Aerojet Rocketdyne, multiple parallel bets, each exploring a different aspect. Material scaling, flight integration. The US strategy is not to pick one winner. It's to fund 10 projects and see which one breaks through. Here's the unifying thread. Every major space power has an active rotating detonation engine program. Nobody wants to be the one still flying 1960s engines when a competitor deploys RDREs operationally. This is not a niche research curiosity anymore, it's a race. And the prize is an engine that changes the economics of spaceflight. Let me show you the math on why. Here's the thing, if rotating detonation engines are theoretically 15 to 25% more fuel efficient than conventional engines, the downstream effects are not linear, they compound. At current Falcon 9 launch costs, roughly $2,700 per kilogram to low Earth orbit, a 25% improvement in fuel efficiency means you need 25% less propellant for the same payload. That's hundreds of thousands of dollars saved per launch. Over a lunar landing campaign, those savings add up to billions. But it's bigger than just fuel savings. Because the engine itself is more compact and produces more thrust per kilogram of engine mass. The entire rocket gets lighter. A lighter rocket needs less thrust, which means you can use a smaller engine, which also means that it makes the rocket even lighter. It reverses the rocket equation's vicious cycle and turns it into a virtuous one. The thermal advantage matters too. In a conventional engine, the chamber walls are exposed to 3,000 degree combustion gases continuously. You're fighting heat transfer into the metal every millisecond. Cooling channels, regenerative cooling, careful material selection, it's an endless battle. In a rotating detonation engine, the detonation wave passes each point so quickly that the average heat load on the walls is actually lower. The wave is a pulse. It arrives, detonates, and moves on. In between waves, the wall has time to shed heat. This is fundamentally different from steady-state combustion, and it's why Astrobotic's engine had no damage after 300 seconds. The metal wasn't getting cooked the same way. And then there's the disruption angle, the one that makes conventional launch providers uncomfortable. If an RDRE-powered rocket can deliver the same payload to orbit for 25% less cost per kilogram, purely through propellant savings and lighter vehicle mass, then a new space company with RDRE technology could undercut every launch provider on price. SpaceX's reusability advantage becomes less decisive. Not irrelevant, reusability still matters enormously, but if someone else's expendable RDRE rocket is cheaper per kilogram than a reused Falcon 9, the competitive landscape shifts. That's the long-term play. But where do these engines actually go? What do you do with them? Let me give you 3 concrete applications, and the third one is what NASA isn't talking about publicly yet. Application 1. Launch vehicles, the obvious one. First stage boosters benefit from the higher thrust to weight ratio, smaller, lighter engines for the same thrust at liftoff. Upper stages benefit even more. RDREs excel in vacuum. No bell nozzle constraints. Pair an RDRE with an aerospike and it auto-adapts from sea level to vacuum. Efficient across the entire ascent. Astrobotic's plan is to integrate the Chakram into the Zogdor VTOL, vertical takeoff and landing, reusable rocket. The vision is an operational reusable vehicle powered by RDREs within 3 to 5 years. Application 2. Hypersonic vehicles and missiles, the military play. RDREs are compact, they produce high thrust, they can throttle across a wide range, perfect for hypersonic cruise missiles and drones operating at Mach 3 to Mach 5. An RDRE-powered hypersonic vehicle doesn't need a scramjet's complex inlet geometry and supersonic airflow management. It's mechanically simpler, more robust. India's D-Propulse, China's programs, and US DARPA programs are all explicitly targeting hypersonic applications. The military RDRE will likely fly before the commercial one. Missiles have shorter development cycles and bigger budgets when national security is on the line. Application 3. Deep space and interplanetary missions. This is where the math gets most compelling. For missions beyond Earth orbit, every kilogram of propellant saved is 2 to 3 kilograms of mission capability gained, because you don't have to lift that propellant out of Earth's gravity in the first place. Lunar lander descent and ascent engines. Astrobotic's own interest, better engines for landing on the moon. Mars transfer stages, 25% less propellant for the same transit time to Mars. Outer planet missions, the efficiency gain compounds over longer burns. A mission to Europa or Titan that carries 25% less fuel can carry 25% more science instruments. And then there's the long-term possibility nobody's talking about. Pairing a nuclear thermal or nuclear electric propulsion system with a rotating detonation engine as the chemical stage. The nuclear system handles deep space cruise. The RDRE handles launch, landing, and high thrust maneuvers. It's the holy grail of in-space propulsion architecture. But that's another video. The timeline is becoming clearer. Military applications in the next 3 years. Commercial launch in 5 to 7. Deep space in 2030s. This is not a 50-year horizon. This is happening now. But there's a problem, actually quite a few problems, and nobody in the industry wants to admit how serious they are. So what's standing in the way? Astrobotic fired 4,000 pounds of thrust for 5 minutes. That's a record. It's genuinely impressive. But an orbital class rocket engine needs hundreds of thousands of pounds of thrust, scaling up from 4,000 to 400,000 pounds while keeping those detonation waves stable. That is a physics nightmare. More thrust means a larger annular chamber. A larger chamber means more detonation waves interacting. More waves means more interactions, more instability modes, more ways for the entire thing to fall apart. Combustion instability has killed rocket engine programs before. The F1 engine for the Saturn V spent years fighting instability problems, and that was just conventional combustion. Then there's material fatigue. 300 seconds is a world record. An orbital launch burns for 3 to 8 minutes. A lunar lander descent burns for 10 plus minutes. Deep space burns can last hours. The vibrational environment of continuous detonations is unlike anything conventional engines experience. Materials that survived 5 minutes might fail at 10, might fail at 15. We don't know yet because nobody's run one long enough to find out. There's also the valley of death, the funding gap between a successful lab demonstrator and a flight-ready engine. You need flight heritage before launch providers will even trust your engine. But you can't get flight heritage without flying. It's catch-22, and that has killed countless propulsion technologies. Astrobotic's plan to integrate Chakram into an operational vehicle is a bridge across that valley, but it's a high-risk bridge. And here's the honest truth about incumbent inertia. SpaceX, ULA, Arianespace, Blue Origin, they have invested billions of dollars in conventional engine programs. Raptor 3 is an engineering masterpiece. BE-4 is flying. The RS-25 has decades of flight history. Nobody is going to scrap their engine program overnight for a technology that is still proving itself at scale. The transition, when it happens, will be gradual, and it will be fought at every step by organizations that have built their entire architecture around conventional engines. So here's my honest forecast. RDREs will not replace conventional engines in the next decade. They will coexist, first in niche applications, upper stages, military platforms. Then, as the technology proves itself, they will creep into mainstream launch. The 2030s are when this gets interesting. The 2040s are when it might become dominant. But the trajectory is set. The physics is on the side of detonation propulsion, and the global race means nobody can afford to be the last one to solve it. Here's what I keep coming back to. A small team in Pittsburgh on a modest budget working across a few offices just fired a rocket engine that, if the math holds, is fundamentally better than anything we've been building for 60 years. Not 5% better, not 10% better, but potentially 25%. And they did it on their first try. The rotating detonation engine is the first genuine paradigm shift in chemical rocket propulsion since the Apollo era. We are watching the proof of concept era end and the operational era begin in real time. The question isn't whether RDREs will fly, the question is who flies them first, and what that does to the balance of power in space. If you're a SpaceX, a Blue Origin, a ULA, you're not worried yet. But you should be paying very close attention. So, what do you think? Is this the future of rocketry or another propulsion technology that stalls in the valley of death? Drop your take in the comments, and if you want to go deeper on any of the engines I mentioned, Raptor 3 aerospikes, nuclear thermal propulsion, let me know which one. Thanks for watching, I hope you enjoyed the video, and if you did, consider subscribing.